Okay, I'm pleased to welcome Eric Poisson today, our speaker. Eric has received his PhD from the University of Alberta and then did postdoc at Caltech and Washington University in St. Louis before he took up into residence in Guelph, where he has stayed ever since, except for occasional sabbaticals here at CITA, I guess.
Right, and lived happily ever after. Thanks, Harold. Well, thank you for being here this afternoon, and more generally speaking, thank you for the warm hospitality that I've been enjoying since I came here on my sabbatical. There were a few weeks in Paris ahead of time. I was worried that this would pale in comparison, but it's a pretty fun place. So thank you for all of that. It's been really fun. I want to talk about tidal dynamics and tidal deformations of compact bodies, focusing on black holes mostly. Let me give you a little bit of the context for this, and then I'll get on with the work itself. There's been quite a bit of work recently on tidal deformations and the tidal dynamics that takes place when you have compact binary systems involving neutron stars, for example. There's been work on this for a long, long time, spanning many decades, but I think there's been a real surge of interest since Einar Flanagan and Tanya Hinderer pointed out that it might be possible to detect tidal effects in neutron star mergers in gravitational waves before the merger actually happens. The idea is this: it's a pretty simple idea. So you have two rapidly revolving neutron stars, close to merger but not quite there yet. Each neutron star is tidally deforming the other one, and this tidal deformation is changing in a subtle way the orbital motion of the two stars around each other. And because it's the orbital motion that's producing the gravitational waves, if you go and look at the waves in a detailed way, you can see the imprint of this in the form of the waves. They did the quantitative analysis, fairly preliminary at first, and discovered that there was a fighting chance for a detector like Advanced LIGO to be able to see this effect. This was followed up by a lot of work that refined mostly the nature of the neutron stars, made better, more realistic models for the neutron stars, and then other people looked at more realistic aspects of the detection, and I think the jury is still out to see whether Advanced LIGO will really be able to measure this effect, but there's a good chance that it might. And that's really nice, because if you see an imprint of the tidal dynamics in the gravitational waves, you have a chance of measuring something about the internal composition of the neutron star before all the messy details are revealed in the merger. So a lot of work has gone into this, and that provides a lot of the motivation for what I've been doing. It's been known for some time that if you are thinking of sources of low-frequency gravitational waves, and in particular looking at extreme mass ratio binaries, so a small black hole orbiting a supermassive black hole, that the tidal dynamics is actually significant. So here it's the small black hole that's producing a tide on the large black hole. That tidal interaction leads to a transfer of angular momentum from the black hole's rotation to the orbital motion, and that can be shown to have a significant impact on the in-spiral. You can produce a large number of wave cycles through this effect, something that of course will be measured once LISA, or some evolved version of LISA, is launched. Yep.
The realization that tidal deformation may be observed, was it first pointed out by analytic calculations?
Yes. The initial calculations were preliminary, so you had to sort of do some simple modeling of the neutron stars, and it was mostly based on, I'll talk about love numbers in a moment, but you just insert love numbers wherever appropriate in the orbital motion and in the gravitational waves, and you can see that this is a parameter that can be measured.
The numerical calculations before that, in principle, already were seeing those effects, no?
Yeah, so of course, if you do the full numerical simulation of two neutron stars, you will see that at some point, at fairly high frequencies, the form of the wave starts to differ from what you would infer for point particles or for black holes or things like that. The interpretation in terms of clean tidal effects is not so clear because, when you do the numerical simulation, you see everything that's there and you cannot disentangle what is tied, what might be something else. I think the analytical calculation made that a lot clearer. But you're right, there was numerical work prior to this, Tagoshi and, Shibata and others did things like that. I've been interested in that sort of thing, and one thing that I started out doing when all of this became fashionable was to look at the relativistic foundations of tides, and people were talking here about love numbers. I mentioned it. I'll mention what they are more precisely later. But I realized at the time that there was no proper relativistic theory of tidal love numbers in the literature, so I decided with my student at the time to go about doing this. And incidentally, in Paris, Thibaut Damour and his postdoc, Alessandro Negar, were also doing that at the time. So simultaneously, we came up with a theory of relativistic love numbers. And there's been further developments since. I won't say anything about this, but Kent Yagi and Nico Younes a couple of years ago discovered a class of relationships that are almost universal among all models of neutron stars that involve the inertial moment of a neutron star, its love number, and its rotational quadrupole moment. I won't say anything about this, but that's a remarkable development that is showing that there's a lot to be learned if you can have access to the tidal interaction of neutron stars. Another development, I won't say anything about this either, is that people led by Damour and his cohort have been looking at modeling tidal interactions with point particles. It seems contradictory, but what they do is to take a point particle action and add terms to it that capture the tidal deformation. So it's a sort of skeletonized way of doing point particles, but with more quantities than just the particle's mass. You introduce the tidal invariance in the point particle action to capture some of those effects, and that's also under
like
intense development. So the point of view, of course, is that your body fundamentally is extended.
Yeah, you're characterizing the interior with more degrees of freedom.
Exactly, and then you collapse it all down to a point. Yeah.
That model that uses the sun.
Yeah, well, people who like that tend to like effective field theories. I know how you feel about those.
Actually, I'm in favor of it.
Okay, so that's good. All right. So let me go on. So I have very modest goals in my work. So I've noted that there's been something like 300 years of developments of tidal theory in pure Newtonian physics that's achieved a great degree of predictability and elegance and completeness. Well, okay. Yes, modulo that. I'll say something about dissipation in a moment. So I just want to do the same thing in relativity, achieve the same degree of completeness and elegance, nothing less. I want to do it for material bodies, but it turns out that black holes are so much easier to deal with that for my talk here, I'll focus mostly on black holes, but I will, from time to time, say something about material bodies. The reason why material bodies are so much harder is mostly dissipation. Black holes give it to you for free, so you never have to worry. So what I'll do, I'll start from the beginning, and I'll review the Newtonian theory of tides to then move on to the relativistic theory. And here I feel very self-conscious because you guys are all sophisticated astrophysicists. So when you do Newtonian tides, you do it for real. Whereas what I'm going to be doing is highly idealized. It's an idealized version of the Newtonian theory of tides, but my purpose is really pedagogical. So you can laugh at me all you want, but what I'm really trying to do here is to step up to the relativistic version, and what I want to convince you of is that if you describe the Newtonian theory in just the right language, you can do that step up with very few alterations except for a few technical, difficulties. But conceptually, I claim that what you can do in Newtonian theory can be ported to general relativity with almost, except for technical details, no conceptual changes. So let's go on. I'm going to introduce a set of assumptions here that will be exactly the same when I move on to general relativity. So I'll place my attention entirely on what I call the body, which is a self-gravitating body, which later on will be a black hole, but for now is just some Newtonian self-gravitating body. I want to consider that body to be placed in a tidal environment, but I don't want to specify just yet what that is. So it could be, the tidal force is produced by a companion body, but it could be 10 companion bodies, it could be a galaxy, it could be whatever it wants to be. I will really refrain from saying anything about the nature of the tidal environment until later. I want it to be very generic, is what I'm trying to say. Body has a mass m, it's going to have a radius r, it would be spherical in isolation, but of course it will be deformed by the tidal forces. I can have rotation in my body, but I don't want to bother with rotational deformation, so I'll include rotation but ignore the rotational deformation. Because my external body, my external matter is remote, something that I didn't mention but was written, I can safely assume that my tidal forces acting on a body are going to be weak, so that the deformation is small. That means that I'm setting myself up to do perturbative calculations. So no tidal disruption here, no violent spectacular events. It's a very tame tidal field. By the same token, because my external matter is way out there, the time scale associated with the changes in the tidal environment can be assumed to be slow compared with the internal time scales that govern the internal physics of the body, so that basically my body is almost always in hydrostatic equilibrium if I'm describing it with fluids, which is what I would do for a material body. I'll be working in the moving frame of my central body, so that's a non-inertial frame that's moving with the body. And the origin of that frame is going to be the center of mass, so everything that I'm doing is going to be about the center of mass of the body. And throughout the description of Newtonian tides, except for the very end, I will restrict my attention to a small neighborhood. I call it the domain N, a small neighborhood of the body. So here's the body, and here's the neighborhood that might extend maybe, 20, 25, 100 radii of the body, but doesn't extend beyond that. And in particular, it doesn't extend so far that it includes the external matter. The external matter is way out there, outside of the domain. What I want to do is to solve the equations of Newtonian gravity inside the domain with some information coming from the outside, but no direct knowledge about what's going on outside. That's the setup. And again, keep in mind that what I'm saying here will be exactly what I'm going to be saying in the relativistic setting in a few minutes. Okay, so I'm working in N, my limited domain that excludes the external matter. What I want to do is to describe the gravitational potential associated with my tidally deformed body. I will split it in terms of the potential sourced by the body itself, and that will be the equation that governs that, Poisson's equation with the density on the right-hand side. And a part that's coming from the outside is sourced by the remote matter. And in my domain N, there's no density associated with the remote matter. So here I'm solving Laplace's equation for the external potential. In fact, I don't really need to solve this equation because all I can say is that because the external length scale is so large compared with the length scale associated with that domain, I can presume that the external potential is going to be varying slowly, and I can express it as a Taylor expansion away from the center of mass. So x is the position vector from the center of mass. I'm going to take whatever function that is and do a Taylor expansion, 0th order term, linear, quadratic, and I could keep going if I wanted to. This, of course, doesn't do anything. It produces no gradients. This is linear, and that's responsible for the center of mass acceleration of my body. If I'm working in the body frame, I can take this out. It's not producing any local effects. What's left over is what starts at quadratic order, and this is the term that's responsible for the tides. It's a quadratic potential. After I take one gradient, it's going to be a pattern of force that's going to be linear in the displacement away from the center of mass. That coefficient in front is going to be the sole provider of all the information I need about the tidal environment. Of course, I get it by calculating two derivatives of the external potential, evaluating that at the center of mass. But for my purposes, this is what is providing all the information I care about, the tidal environment. And for my purposes, it's just a free function of time, or a collection of free functions of time. It's a tensor. I call it the tidal tensor. For technical reason, associated with this equation right here, it's actually a symmetric trace-free tensor. 5 independent components. One thing to note here is that this is not determined, the tidal tensor is not determined by the field equations limited to my domain n. In order to specify what that is, which I'll do in the 4th step of the construction, I have to go outside the domain and really specify what is producing this in the first place. But for the time being, working exclusively in my domain n, what I have is a gravitational potential here that is described in terms of arbitrary functions of time that provide the information about the tidal environment. That's the language that I'm introducing to describe my tidal environment. It's all in here. And so long as I don't choose or care to specify what that is, I just keep it arbitrary, and that describes my completely generic tidal environment. At least to leading order in this expansion, I could add higher order multiples if I wanted to. All right? So that's how I characterize the tidal environment in Newtonian physics. The hard part of tidal physics is to describe how the body will deform under the action of those tidal forces. So there are lots of ways you can measure the deformation. Because I'm doing gravity, what I'm going to do is to measure the deformation through the deformation of the external gravitational potential associated with my body. And that deformation will be measured by the quadrupole moment tensor that I can calculate from the pattern of density inside the body. The whole game in tidal theory is to relate this, which measures the deformation, to this, which is a specification of the tidal forces. And that's where all the hard work is. You have to decide what the body is. You have to define its composition, its stratification, all of those details, the dissipation that goes into that. But whatever you get, at least in simple situations where the body is an isotropic fluid or something simple, in every case, you will get a relationship like this, which is basically just a linear relationship between the deformation and the applied tidal field. You get a few quantities in front. The 5 powers of the body radius just comes for free by dimensional analysis. The number in front is where the details are all contained. So all the details of internal structure that I choose not to specify here will be contained here. So if you do something very simple like an incompressible fluid, or if you do something very complicated like an Earth that has a fluid core, a solid mantle, and all of that, you'll just get different numbers for K2, and that's all that's all there is in terms of difference.
So this is like linear response theory, but
it is.
Linear response theory would express the other side as a convolution over past time.
Right. So here I've simplified that convolution. It's an approximation.
What is, the viscous delay is something which involves lots of complication. But is this approximation okay? That you just say there's one time that I can go back?
Yeah, no, I say the answer is probably it's not actually known very well, but it's pretty clear that the tidal response depends on the frequency that Poisson has. It's a delay. Depends on the field that you're putting on.
Sure.
Yeah, and you can think of this as a zero frequency limit.
Exactly.
No, I see that it's the zero frequency limit. It's just that it seems to me that there is a framework for all of this, which is linear response theory, and that would tell you what the susceptibility
is.
is.
A big book on this, but actually doing it for real materials, all these theories don't work.
Empirical calibration is the only tidal limit for nearly circular orbits to an archetype.
And in the case of the Earth, right, you have timescales ranging from hours to decades. And we know
that makes sense.
And they don't, and the Qs that you get out or the K2s even vary.
Right. So I wouldn't claim that this is necessarily a good approximation. I think the biggest uncertainty is the dissipation mechanism that you have to put in order to produce this delay. But it does capture something very essential. So something I wanted to highlight is that the measure of the tidal deformation, the scale-free measure of the tidal deformation is contained in K2. That depends on the internal structure of the body. But another very important quantity here is that delay that we were talking about. And that's just a statement that the tidal deformation now will depend on what the forces were doing a little bit earlier. And in general, it could be written as a convolution involving more than just one time. But here I'm choosing to simplify this just through this one time parameter that describes how much delay there is between the action of the force and the response itself. And that's very important. You will get something like this. An effect that's captured by this will come whenever you have dissipation in your system, and it turns out that to have dissipation is crucial for dynamical consequences, because it's that delay or that dissipation that's responsible for the misalignment between the tidal bulge and the direction of the companion body. And it's that misalignment that's allowing the tidal forces to apply a torque on the body, and that's how you can have a transfer of angular momentum. So it's very important for my purposes, at least in Newtonian theory, to capture this somehow in the simplest way is through this viscous delay effect. So you can think of K2 and tau as being quantities that capture internal details, K2 about composition and tau about what is producing that dissipation that is crucially important here for tidal dynamics. So once you have a complete description of the tidal deformation, and I claim that, to the leading order in all this, this is pretty complete. It captures everything you need to have. Then you can ask questions about dynamics. You can ask, for example, how is the tidal forces torquing the body, and what is the exchange of angular momentum between, for example, an orbiting moon and a rotating Earth? And well, again, that depends on your underlying theory. You need a theory to be able to calculate the angular momentum in your rotating body. So if you do fluids, you have access to all this machinery. But again, you can sort of write down generic relationships among these things, and they will look something like this. So here, I could have written an expression right here involving a vector, angular momentum vector, and a tidal field that would have all the tensorial components. What I decided to do here, just to show an equation that can be interpreted a lot more easily, is to specialize the tidal environment to one that is rotating rigidly with a fixed angular velocity. So I could be thinking of a companion body that's moving around a circular orbit, but I could be thinking of anything that is rotating with an angular frequency that I'm calling omega tide. If you make this assumption of fixed angular rotation, then you can work out the components of your tidal field, and you find that some are actually fixed in time, some oscillate at twice that frequency. And when you plug that into your big formalism to calculate the rate of change of angular momentum in your body, you find an equation like this. What this equation says, crucially, is that the sign of the rate of change of angular momentum, of the spin angular momentum, is dictated by the relationship between omega tide and omega body. So if the tidal field rotates faster than the star is rotating, you spin it up. If it's the other way around, you spin it down. And of course, if you've achieved equality, then you have an equilibrium and the spin stops changing. So you have this proportionality between the difference between the two angular frequencies. You have the r to the fifth that we had previously. The effect is quadratic in the tidal forces because it's a torque, right? So you need the force and you need the displacement, and the displacement is linear in the force. So that's why we have the two powers of the tidal field here. And what really matters for the effect is the component of the tidal field that oscillates at twice the orbital frequency. Of course, we need a time dependence to make this happen. Crucially, though, what's even more important than all of this is what appears in front. We need both K2 and tau to have an effect. We need K2 because we need the deformation in the first place, and we need tau because we need a delay. And as I said just before, you need a delay to produce this the misalignment between the bulge and the direction of the companion body, and it's this misalignment that's allowing the tidal forces to apply a torque on the body. So you need a displacement, and you need a form of dissipation to make all of this happen. Other than that, the scalings are sort of obvious, apart from some overall numerical factor that we don't really care about.
So how general is this constitutive relation which is being hypothesized, because in cosmology, the key to developing the angular momentum is actually the mismatch of the internal Q and the external epsilon. And so that's the thing that was the tidal torquing, which is supposed to be the origin of all of the angular momentum.
In the universe,
and
yeah.
so that says that K2, if there is such a thing, would be a complex response tensor to tensor with many, many more coefficients than a diagonal. So
oh yeah,
that's
sure.
Another extreme approximation here.
Well, I mean, to begin with, I've assumed
it's forcing. Okay. Right.
yeah, and I'm assuming an isotropic response. So of course I could introduce a K2 tensor that will relate all the components to all the components, and that would be a more general setting to presumably.
Yeah, I believe,
Yeah, probably. Yep.
The original assumption was that the tidal timescale is very slow, right?
Yep.
So that sounds like there's something with the tau.
Yeah. So the assumption is that that you could do a Taylor expansion here, so that the tau dependence is much that the t dependence is a lot slower than the internal dynamics, so you can safely do a Taylor expansion in the time. So that's why the time ends up, the delay ends up being as a coefficient in front. Yeah.
Well, people seem to think that nobody's talked about
Well, another issue here is that you're assuming there's no resonance between the external tidal field and some normal node.
Right, and that's my slow assumption. Yeah, yeah. If I want to do dynamical tides, of course, I would have to do all the modes, the mode analysis. Yeah, that's right. Yeah, and for me, that's a very good assumption for my purposes. Okay, so the last thing I'm going to do in Newtonian theory, if Dick and Don will allow me.
Your talk is so stimulating.
Yeah, obviously, yeah. So the last thing I want to do in the Newtonian theory is to finally specify the tidal environment. So I've taken some pains not to specify what it was, except for some, rotation assumption to simplify the equations. But the point I want to make is that if I do want to specify the tidal tensor, finally I have to leave my domain. I have to identify what's out there, and I have to do the calculation. What I like about this setup is that I can develop the whole formalism with a generic tidal tensor. And whatever the application is at the end, I can plug in what is appropriate for any given situation. But at the end, I have to go and identify what that is. If I do the simplest thing, go outside and decide that, well, there's one companion body going around my central body, I can say that, well, the external potential, after all, is going to be something like this with an external mass at some external position. I can calculate those two derivatives, and I can finally calculate those components that appeared previously. For example, this one, which is very important, and of course I'm learning that the tidal field is proportional to the external mass and inversely proportional to the third power of the separation. And based on the Newtonian dynamics between my two bodies, I can also calculate the frequency, angular frequency of the tidal field, which of course happens to match the orbital frequency between the two. And at that stage, everything is complete, and I have a complete story. If I decided to change my tidal environment, I could just repeat this last step, but I wouldn't have to touch the earlier parts of the story, which were formulated entirely in terms of this. Okay, so that's the Newtonian theory. Did you have a question? Yeah. Oh, the dipole term in the expansion of the external potential is just responsible for the acceleration of my central body. And if I work in that frame, it cancels out. Yeah. Continue to think about dipole, because that will play a role in the GR context. Okay, let me go on to relativity. All my assumptions are exactly the same. In particular, this statement that I made that I wanted to work in a limited domain around my body will be the same. All the remote matter causing the tides are out there. I don't want to say what is out there for the time being. I will come back to that as the last step, as I did for the Newtonian thing. So this could be a black hole. This could be a neutron star. For the time being, I'm not going to specify what that is. And I'm working in the same domain that I specified previously. Of course, now I'm doing general relativity, but my same assumptions about how weak the tidal interaction is, how weak the tidal forces are, how weak the deformation is, I apply. How slow it is, I can apply in the same way. And if I work exclusively in the domain n, that means that I can do linear perturbation theory. What I can do is to start with an unperturbed metric that would describe, in my context, a slowly rotating body. I want to include the rotation. That will be part of the story, to which I add the perturbation that comes from the tidal field. But that perturbation is weak, and I can obtain this perturbation by solving the linearized Einstein field equations around the metric of my unperturbed body, which is my slowly rotating, otherwise spherical body, because I'm ignoring, as I did previously, the rotational deformation. I split the perturbation in terms of a body piece and an external piece. The body piece will be sourced by the deformation of the fluid inside the body, deformed by the tidal forces. The external piece is sourced by nothing because its source is outside the domain. And because I'm doing linear perturbation theory, well, I do have the right to do the split, which is very convenient here. In a Newtonian context, I could specify the external solution in terms of those free functions of time that I call the tidal tensor. In GR, I have more degrees of freedom, and in fact, I find here that I can describe the tidal environment completely, generically, in terms of two tidal tensors. The E1 that we saw previously that has a direct analog in Newtonian physics, and a new one that only exists in relativistic physics. This basically captures the gravity aspects of the tidal interaction, and this captures the gravitomagnetic aspects. So this is associated with motion. This is associated with, static gravity, so to speak. So the point is that because I'm in GR, because I have more gravitational degrees of freedom, I have to double up the specification of the tidal environment with two tidal tensors instead of just one. If you want to be very fancy, you can think of those guys as being, in some various limits, in various ways, components of the curvature tensor. If you're really fancy, you call it the Weyl tensor outside the body. I don't need to really do that. I can simply think of these guys as functions of time that are completely arbitrary and undetermined if I only solve the field equations inside the domain n.
So to do the splitting here, you still have to choose a preferred notion of time everywhere. In what sense are these gauge invariant? In what sense do you choose your preferred notion of time in the problem?
Well, so the notion of gauge invariance I'm using is the one that's really appropriate to perturbation theory, where you start with a background, a background solution in your favorite coordinate system. Then you add a perturbation, and part of that perturbation could, in fact, describe, small coordinate ripples. So it's gauge invariant in the sense that it doesn't matter, which ripples you put in, but it does matter in the sense that you need to start with, it makes a statement about which starting coordinate system you had for your unperturbed metric. So it's gauge invariant in that sense.
You're going to be choosing, I guess, since you, in some sense, you're going to want to think about perturbing on the space-time which did have a very definitive notion of time.
Right.
Because it had a time symmetry or something.
Yeah,
So
it's just that.
And then a small perturbation off of that doesn't impact E of B.
That's right. That's right. That's right. Yeah, so in practice I use Eddington-Wilkenstein coordinates so that I have a good slicing that I can take all the way down to the black hole. And that's right, these guys would not change if I were to make a small coordinate transformation on top of that. Okay, so my favorite way of thinking about these guys is simply that it's a part of the metric that you cannot determine by just solving the equations, the Einstein field equations locally, but that you can eventually determine by going beyond the domain and incorporating all the information that you have about the remote matter. So apart from the doubling of the number of degrees of freedom for the tidal field, it's pretty much the same thing we had in the Newtonian theory. Step 2 in Newtonian theory was to relate the tidal field, relate the deformation of the body to the tidal field. Here you have to do it all over again, but now in general relativity. So in particular, whatever modeling you had to do in Newtonian theory to calculate the love numbers, you have to do it again, but now relativistically. So you have to come up with your favorite body model for the body and calculate the deformation inside, match it to the deformation outside. And that's the calculation that in Newtonian theory would reveal the love number. Here, the calculation reveals two love numbers because you have two independent tidal fields, the E field and the B field. So when you do all of this, starting from a model of the body, you end up determining two types of love numbers, one that comes with the E field, the other one that comes with the B field, so that the tidal description then becomes twice as rich in GR as you had it in Newtonian gravity. All of this modeling is, requires a lot of details. If you choose your body to be a black hole, none of those details matter anymore. All you have now is an event horizon. What replaces the internal calculation matched at the surface to the external calculation, what replaces all this is just an external calculation that is now required to be well behaved at the event horizon. And it so happens that if you want all of this to be true, if you want a perturbation that is well behaved at the event horizon, you have to switch off completely that body part of the metric perturbation, which is saying the same thing as saying that the love numbers of a black hole are 0. And sometimes I say this and people get very upset. Sometimes I say this and no one bats an eyelash, so it's hard to know where it goes. I think initially the statement seemed provocative and some people in my field seem to resist it, but I think now everybody's got used to the fact that, well, that's just the way of life. Black holes do deform under tidal forces, but they deform just as much as they have to given the presence of an external field. They don't produce their own additional deformation to that. That's what this is saying.
What do you actually mean when you say that it well behaved at the event horizon?
That if you look at the perturbation field as a tensor field, that it has to be regular at the event horizon. And what you find is that a generic perturbation would in fact be singular, and you have to take that piece out. Otherwise, you don't have a black hole. Right? If you really do the work for a black hole, yes, you have a question?
Is that a special property of event horizons, or is it just null surfaces that are something back to?
It has to be a stationary null surface. So that's not quite saying the same thing that it has to be an event horizon, but in my context it is. Right. So if you actually do the work, you end up with something like this. And here I'm just showing a part of the deformed metric. So that's the metric outside the black hole. That's just the time-time component. I just wanted to show a few things. So let me just describe how I do the calculation very briefly. First, I start with a Schwarzschild black hole. That's what this line represents. Then I add rotation as a perturbation. Then I add the tide as another perturbation. And then, because I was curious about the coupling between the two, I let the rotational deformation, the rotational perturbation and the tidal perturbation coupled together. And I solve for that by going to second order in perturbation theory. I don't do second order in rotation, I don't do second order in tides, but I do second order in the coupling between the two. You don't see the pure rotational term here because it would show up in the space-time components of the metric. But you see here the pure tidal deformation. That's this term right here that has pretty much the same structure you saw before in Newtonian theory, but now we're adding relativistic corrections to that. Everything else corresponds to what happens when you couple the rotation, the slow rotation, to the small tides. And technically what happens is that the rotational perturbation is a pure dipole, L equals 1. The pure tidal perturbation is a pure quadrupole, L equals 2. When you couple the two, remember your Clebsch-Gordon coefficients, L equals 1 plus L equals 2 gives you all the L's from L equals 1, 2, and 3. So you generate dipole terms, quadrupole terms, and octupole terms. The quadrupole term is right here. It involves the phi derivative of the original tidal potential plus a bunch of relativistic corrections. This is the dipole term. It's linear in the displacement away from the center of mass. It involves the magnetic tidal tensor. And it involves, of course, the, what I define here to be a dimensionless angular momentum vector for the black hole. It's the spin angular momentum vector divided by the mass squared in relativistic units that makes it dimensionless. The dipole will come back to us. It doesn't play much of a role in terms of tides, but it will say something when we look at the motion of the black hole a little bit later on. This is the octupole term. It's cubic in the displacement, and this mess of indices over here, the angular bracket here just means take all of those indices over here, make them all symmetric, and then take out all the traces, and that guarantees that you have a function here that can be expanded in L equals 3 spherical harmonics. So we have a quadrupole, pure quadrupole, then an augmented quadrupole from the coupling, and then we get the octupole deformation, and on top of all of this, we get a dipole. So the quadrupole plus the octupole means that your tidal pattern, for example, on the event horizon, you can take the symmetric that I just displayed and use that and the other components to calculate how the event horizon itself deforms. And you can represent this in various ways, like a color pattern like this. But the point is that because you have a superposition of quadrupole and octupole deformation coming from all those couplings, you have a pattern that is a bit richer than what you would expect if it were just a pure quadrupole. So this is a front view, this is a back view. The bulging occurs in this direction. The companion body would be somewhere around here. But on the back, you don't have exactly a symmetric pattern. You have something a little bit different. It's been exaggerated here for the purposes of illustration. But the point is that you're supposed to identify here the fact that it's not a pure quadrupole, but it's a quadrupole plus an octupole. So that is all about describing the deformation of my black hole. And as I did in Newtonian theory, I'd like to go beyond this and try to extract some dynamical consequences. And in the Newtonian picture, I was looking at the transfer of angular momentum between the orbital motion and the spinning motion of the body. Here I want to do exactly the same. So I'm going to display a formula that describes the rate of change of the black hole's own angular momentum as a result of the tidal interaction. That can be calculated. There's an entire formalism that goes back to the early 70s that allows me to calculate all of this very easily. I don't have to worry about a source of dissipation. As we said just earlier, the event horizon is doing this for free without having to specify any internal physics. So there's a whole formalism that can be relied on. So I'll display the formula on the next slide. I just wanted to introduce the formula with the same sort of tidal field that I discussed previously in the Newtonian case, a tidal field that's just assumed to rotate rigidly with its own angular frequency that may or may not be the same as the black hole's own angular velocity. So the E tidal field has exactly the same structure we had it before, some time-independent components, some time-dependent components. The B field, which comes from gravitomagnetism, has a different structure. It has only one time-changing component, and this one oscillates at 1 time the frequency. This one was oscillating at twice the frequency. I'm not going to specify what those amplitudes are because I just want to make the smallest set of assumptions I want to make about the tidal field. So when you plug all of that in and calculate the rate of change of the black hole's angular momentum in terms of some well-defined time on the event horizon, you get something like this. And I'm inviting you here to compare this to the Newtonian expression we had before. Well, it's a bit more complicated.
Part of the fact that the source terms for E and B are outside of the region, is there a simple way to characterize relative magnitudes here? In particular, at what point does the accumulation of information actually have any impact on cosmology, for example, because of some kind? I mean, the standard picture would be, well, I could go into the Newtonian gauge and effectively I'm essentially dealing with phi. That will not be the case if there's weird forms of matter.
Right.
But I'm just wondering if, you know, what I should be thinking about in terms of the magnitude of B relative to E.
So generally speaking, it's true that B will be suppressed relative to E by at least one factor of V over C. If you had cosmological matter, the assumption I would make here is that, well, you have the scale of the black hole itself, then you have the scale of the black hole plus the external matter. And way beyond that, you would have the cosmological scale, and I would assume that the cosmological scale, the cosmological aspects decouple entirely from the local dynamics, and that is something you see very well in the Newtonian gauge in cosmology.
Yeah, I was just thinking of if the matter had an anisotropic stress, whether that would have a B response or something. I mean, you know, usually we aren't really dealing with a lot of anisotropic stress.
Right, so I haven't thought about this. That's an interesting question. Yeah. Anyway, so that's the relativistic formula that applies to a black hole. That's the Newtonian formula we saw before. It's a bit more complicated. What you see in here are, what you see in here is everything that comes from the tidal field. And this is the dominant term. All of those here are suppressed relative to the dominant term by factors of V over C. So let me parse this out a little bit. So we have the same dependence on the difference between the two angular velocities. So that's the angular velocity of the tidal forces, the tidal field versus the angular velocity of the black hole itself. We have the same relationship here as we had previously. So we spin up the black hole if the tide is rotating faster than the hole is doing, and the other way around if we have the opposite. So we have that. We have the 2 powers of the tidal field here plus relativistic corrections. So everything that's extrinsic to the black hole is reproduced in the relativistic formula straight from the Newtonian formula except for corrections. The intrinsic dependence looks a little bit different. Here I had 5 powers of the radius and 1 power of the tidal, the viscous delay. Here I have 6 powers of the total mass. Well, one thing to note here is that if I make this assignment over here between the Newtonian quantities and the black hole quantities, I get, you know, apart from relativistic corrections, I get a perfect match between my 2 formulas. And that, you know, pleases me to no end because, you know, what could be more different than a black hole and a viscous Newtonian body, yet in terms of their tidal dynamics, you can map one to the other without losing too much information. Well, does it hold up? Well, sure, right? I mean, I can associate 5 of those, you know, this m to the 6, I can take 5 of those, assign it to the body radius. That certainly makes sense. That's the radius of the black hole. And you have something with the dimensions of time in relativistic units. It's the same thing as dimensions of mass or length. So I can take the remaining m and assign it to k2 times tau. And that's the only time scale I can associate to a black hole anyway. So it sort of makes sense, relativistically speaking, that whatever is producing the viscosity that I need for my tidal interactions is produced by the event horizon with its own scale of the mass. And yeah, usually I get this reaction. So what's happening here? In Newtonian story, I said that we need K2 for a non-zero displacement, a non-zero deformation, and we need the tau for dissipation. Well, what I really need is the 2 of them together, and maybe I don't need to take them apart, and maybe I shouldn't take them apart if I'm talking about black holes, because if I take K2 apart for a black hole, I know it's 0, but K2 times tau here in this, you know, in this match is declared to be non-zero. So the way I like to think about this is that, well, this is not 2 separate parameters. It's just a combination that should always stick together. And that combination that always sticks together is of order of the mass. And if you make this assignment, you get something that matches perfectly well. Apart from relativistic corrections, and that allows you to say that a black hole is no different from a Newtonian viscous body in terms of its tidal response, at least to first order in relativistic physics. I like that.
How could K2 tau be non-zero when K2 is 0?
That's what I'm avoiding trying to face. But I can always say that in the limit, where I go from Newtonian theory to a black hole, K2 goes to 0, tau goes to infinity, and they go together so that the limit is a...
Try and give that interpretation to Love's basic formula of T minus tau.
I wouldn't want to do that, no.
No, I don't.
No. That's right.
So what are you interpreting the dissipation as? Is the horizon going off gravitational waves? Is that what you're interpreting?
No, it's just the fact that whatever goes in never comes out, right? So you have an automatic source of dissipation. And you can push the analogy a lot. I'm sorry?
An automatic sink.
An automatic sink, exactly. And of course, you have people who did the membrane paradigm who pushed this description, a lot farther, and you can describe the null generators of the event horizon as the streamlines of a fictitious fluid that is governed by a Navier-Stokes type equation with a fluid with a viscous term that that basically does all of this. So,
Which I guess begs the question, if you were, I don't know if you explored this, but if you move into more of the membrane paradigm, take the appropriate limits of these governed by these Stokes equations and how they might dissipate the field coming in from the tide, the external tide, do you reduce the sort of results from that?
well, yeah, I think you have to. I mean, I never really applied the equations of the membrane paradigm directly, but I'm basing everything that I do on the optical equations, and they did everything that they do on the optical equations, so it's got to be.
If both sides are right, you'll be able to bring them together. The question, I guess, is on the membrane paradigm side, that intuition of what you call a fluid and what you mean by dissipation may not match up in the end to coming from the other side, which you might want to call a dissipation. That's what I'm curious about.
Yeah, it's possible. It wouldn't be the first time the membrane paradigm just doesn't
names to things, right, in the membrane paradigm, which don't necessarily have
to match to.
in every analogy.
That's right.
You want them to do.
That's right. Chris?
You put a black hole in external electric charge distribution.
Yep.
Induced electric dipole moment.
Yep. That's a question. Is there an induced dipole moment? Yeah. Yeah. And that can be described with the membrane paradigm in terms of a fictitious, membrane with a charge conductivity. Sorry?
Why is there an induced electric dipole moment and not an induced gravitational quadrupole?
Oh, no, there is an induced quadrupole.
I thought you were saying the K2 is
Well, that's what he's saying. He's not
Okay.
saying K2 is 0. He's saying K2 times tau is not 0.
Right. No, but even if K2 is 0, there's still a deformation to the black hole.
Yes.
But you cannot distinguish the intrinsic deformation of the black hole from the tidal field in the first place. So, but there is still a deformation, so there's still a quadrupole moment. Yeah. Okay. So I'm running out of time, so I'll just speed up through the technically demanding part of this whole problem, and that would be to finally go out of that domain N and identify the external matter and determining the tidal tensors for that situation. That's complicated in this case because if you're going outside the domain and starting to include external matter, now you have to leave the confines of linear perturbation theory and you have to face doing something nonlinear, which, at best of times can be a challenge. The way out for me is to assume that the mutual gravity between the external matter and the black hole can be weak and can be described in terms of a post-Newtonian approximation. I'm not saying that the gravity is weak around the black hole. I'm obviously not saying this, but I'm saying that the mutual gravity between the black hole and a companion can be weak. The motion can be slow, orbital motion can be slow, and I can meaningfully describe this through a post-Newtonian approximation. The idea is that I have a place in my domain where a gravity is very strong, but as I go outside and to the edges of my domain, gravity becomes weak, and I can match the metric out here to a post-Newtonian metric, which all the way down to this innermost circle here is a good approximation. So the post-Newtonian metric doesn't extend all the way down to the black hole because gravity is too strong there, but it's doing fine down here, and the metric that I described previously does fine up to here. There's an overlap that allows me to gain all the information that I can gain about the tidal environment by doing this matching between a post-Newtonian metric that extends all the way down here and my black hole metric that extends all the way up here. I'll skip all of those details. They're fascinating, but I'll skip them. I'll just show you the results, and this slide is awfully busy. Let me highlight things. So I have all sorts of quantities here. So m and chi is the mass and angular momentum, dimensionless angular momentum of the black hole. M prime and chi prime are the mass and spin of the companion body. So here I'm specifically assuming that the tidal environment is produced by one orbiting body around the black hole. V is the orbital velocity between the two, which I'm assuming to be small compared with the speed of light. And then there's more symbols, but they don't matter as much. Q is the fractional mass in the black hole. Q prime is the fractional mass in the companion. Chi bar is some mass-weighted average of the two spins. What I wanted to show is that by doing this matching that I described so briefly, I can calculate all the amplitudes that go into the tidal tensors. And to leading order, of course, I get the Newtonian results back, so the same m prime over r cubed that we had before. But now I get all the relativist, well, I get some relativistic corrections, beyond the point where I don't care to calculate anymore. So this would be a 1pn correction of order v over c squared. This would be a 1.5 correction of order v over c cubed. And all the amplitudes have that structure. I can also calculate the angular velocity of the tidal field itself. I have a complicated expression for this. What I wanted to point out is that it doesn't match the orbital angular velocity for two reasons. We're looking at the time variation in the moving frame of the black hole, and the time coordinate in that frame is not the same coordinate that I would use in the barycentric frame of the two bodies. So relativistic time dilation will create a mismatch between the two angular velocities. And on top of that, my local frame actually precesses relative to the barycentric frame, so I get this extra effect on top. Anyway, I get all of this information, and I can plug that into the flux formula and get something very concrete that tells me how much the black hole is actually absorbing angular momentum. That could be useful eventually in characterizing the tidal dynamics of black holes in concrete situations. I find it very amusing that a few months ago, the Caltech group, together with Cornell people and maybe people here, I don't remember the entire list of authors, actually calculated the effect in a simulated spiral involving rapidly rotating black holes that underwent something like 25 orbits during merger. I won't go into the details of the curve. I'll just point out that they see an effect of a tidal spin down. It's absolute values here, so you see the spin going up, but it's actually going down because it's rotating way faster than the tidal environment is. So the spin is coming down, and they have a hard time resolving this in their simulations, but eventually they get there, and you can compare this to various analytical formula, including one that I produced myself with Katerina Cițianu and Nico Younes a couple of years ago, accurate at 1pn, and you see that, well, the effect is pretty much confirmed, or at least the effect matches the post-Newtonian expansion that you would expect. So instead of blaming this on numerical error, you can safely conclude, or at least you can be confident that they have measured the tidal torquing of the black hole in numerical simulation.
Is the prediction leading order in chi or all orders in chi?
We're having a little bit of trouble with this. So the claim is that the prediction is high order in chi, is to all orders in chi, because the 1.5 terms are linear in chi. So, so the tidal environment is determined to all orders in chi if it's determined to first order in chi at 1.5 pn. And when you bring this information down to the event horizon, you produce higher order terms in chi that are included in the formula. That's a technical point that I'd rather leave out for now, but we can talk about it. Anyway, I've really gone on long enough, so I'll just flash my, my conclusions, too many of them. I just wanted to point out that all the stuff that I've done on slowly rotating black holes, Phil Landry and I are currently trying to generalize to material bodies. And we're kind of stuck at the moment. And we're also trying to improve this tidal torquing formula for black holes from 1 pn to 1.5 pn. And we're stuck there too. So life is good. Hopefully I'll get unstuck before too long. Thank you very much.
Just to map back to the numerical values, so tau of, if I didn't know the answer, I mean, just in your kind of formula, k tau equal to m, if I didn't know the answer in advance, then I would have said for any given body, tau at most can be m, that's not quite enough. If it went down relatively, but because I'll tell you a body of size, it's not going to be bigger than m.
Right.
And k is not going to be bigger than 1 either.
Yeah.
So it's basically as viscous and dissipating as somebody could possibly be and be that small.
Sorry, you're asking whether you could think of a Newtonian body that would have the same scalings? Is that what you're asking?
If I want to map this, let's ask if I want to think about this as some funny fluid, which is just very small and compact. This fluid is maximally responding to these tidal, because otherwise its axis ratio is the same as the tidal tensor axis ratio, and it's lagging by 90 degrees behind the induced strain in order to get a dissipation rate. That gives the black hole is the most viscous thing you could possibly imagine a fluid doing.
It would be pretty extreme, yeah, that's right.
The black hole could be slowly rotating, so the rotation period could be much larger than that. In which case, tau could be a small fraction of the rotation period.
No, this tau is the rotation speed of the black hole. No, tau is just the time scale. It has a lag, it's right. But this is saying that it lags by...
It's not the angular lag, it's the temporal lag.
It's the temporal lag, yeah.
So, if the black hole is slowly rotating, well, that's what you're assuming. It's still a small fraction.
Well, the black hole can be stationary for all that matters. So if you take a stationary tau, a stationary black hole, and just have something orbiting the black hole.
Yeah, but the angular lag, that involves non-relativistically, is the temporal lag divided by the rotation period, right?
No, if it's a static fluid with a sound speed of order c, then the lag at most is m, right? So let's say it's some fluid. If I just want to make it, if I just want to ask what I might plausibly do, I would say I give it a sound speed of order c. Okay, and then I ask what neutrons I have to do to give me such a high dissipation rate. I would have to say it's going to deform by order unity given by order k of 1, k of number of 1, and its induced particles is going to lag behind by 90 degrees to my applied by 1 pound crossing, not 90 degrees, by 1 pound crossing time.
1 crossing time, that's right. Yeah.
Of my induced thing, which is about as far as you can possibly imagine something lagging.
Yeah, I mean, it would be an extreme relativistic fluid, right? Yeah. So, yeah, that's right.
This you can possibly make an object, even if you look at it.
Yeah, yeah.
Didn't you say there was no lag at the beginning? That it was a quadruple?
I'm sorry?
You said there was no lag at the beginning, that the quadruple was actually a constant value?
I didn't say there was no lag, no. I said there's no love number, right.
All right, let's take the discussion upstairs. There's food there.
Yeah, thanks again.